In the improper integrals, we cannot put infinity directly into our equation because there is no such number. So we create a number a and then a number b, and we make a and b approach to two opposite infinities. So in this case, we write it as limit as the number a approaches to negative infinity from a to 0. Since a is the negative part, we have dx over x plus 3 squared plus a 3. We write the same equation. And then we say plus limit as b approaches to infinity. We again write the same equation. This is the logic of improper integrals. And then we evaluate this. We cannot directly put infinity into the equation, so we create numbers a and b, and then we make them approach to two opposite infinities, and we write it as this is. So, if we look at this, we can see that this is the pattern of tangent inverse. So we can write it as equals to limit a goes to negative infinity 1 over root 3 times tangent inverse x plus 3 over root 3 from a to 0 plus as limit b approaches to infinity. Again, we write the same equation because our equation never changes. It's just that our boundaries where it approaches changes. So if you evaluate this, we get pi over 3 root 3 plus pi over 2 root 3, since this is equal to negative pi over 2. When we put a approaches negative infinity into the equation, and this equals to pi over 2 when we put b approaches to infinity into the equation, so we don't get divergent. Instead, we get these numbers, if you do the math, minus pi over 3 root 3. These cancel out, so we get 2 pi over 2 root 3, which is equal to root 3 pi over 3. This is the answer of the improper integral. If you are asked to test the convergence of a function, you should first do the nth term test before anything else. If it passes the nth term test, then you should check if it's a p-series. If it is, then if p is smaller than or equal to 1, it diverges. If p is greater than 1, it converges. If it's not a p-series, then you should check if it's a geometric series. Then, if r is greater than 1, then it diverges or equal to 1. But if r is smaller than 1, then it converges. But if it's not any of these, then you should check for integral test or a test of comparison. Now, how you can determine it by the integral test? For example, we have a function 1 over n times ln n. Now this function is not geometric, is not p-series, and it passes the nth term test. You should always indicate this with a little check mark. So then we need to integrate this. How can we do that? With improper integral. Limit as b approaches to infinity from 2 to b, 1 over x ln x dx equals to, again limit as b approaches to infinity ln x, if you do the integral correct, in the boundaries between 2 and b. So if you put these values inside, you would get that ln b diverges. So then you don't need to check any other part of the equation. It's just enough that one part of it diverges. So then the series diverges by the integral test. This is a tricky one because it's hard to see that this series is a telescoping one. If you apply the trick plus 1 minus 1, you can see that this series is equal to n plus 1 over n plus 1 factorial minus 1 over n plus 1 factorial. Then, if you cancel out these, then you would get, if you simplify that expression, you would get 1 over n factorial minus 1 over n plus 1 factorial. Now, if you put in the numbers, 1 over 1 factorial minus 1 over 2 factorial. Plus, if you put 2, 1 over 2 factorial minus 1 over 3 factorial. Plus, 1 over 3 factorial minus 1 over 4 factorial, and then it goes on like this. So now, you can see that this is a telescoping series. And it will cancel out except the first term and the last term. And our last term is, as limit n approaches to infinity, 1 over n plus 1 factorial, negative 1 over n plus 1 factorial. Since n is approaching to 0, and since n is approaching to infinity, this whole expression approaches to 0. So then we have a 1 over 1 factorial plus a 0, which is equal to 1.